Okay, welcome back to the second video for section 5.2. Now that we have a pretty thorough review of summations, next what we need to do to prepare for our difficult material is we need to connect limits with summations. And we need to look in particular at four specific limit summation problems, and they're going to look crazy at first. Don't worry about it. And we need to run through how to evaluate each of these four. Okay? All right, so again, we're connecting limits with summations, and we're going to be looking at four specific combo problems. All right, I'm going to need you guys to write down the results, not the entire process, but the results for each of these. The first one goes like the following, and this is by far the easiest one. The limit as n approaches infinity. So we have an make a better infinity sign. There we go. So we have an infinite limit. All right, so just kind of put that in your head. We have an infinite limit. Now, what we're taking the limit of is going to look very strange, but over the next few days, you'll get used to it. It's 1 over n times the summation from I equals 1 to n of the constant 1. Okay? So what I need you to notice is where we have an n, so I'll choose a highlighter tool here, our limit has n going to infinity. This weird fraction out front is 1 over n, and the top number in our summation is also n. So that means each of those n's is going to be approaching infinity. But our summation is going to be in terms of I. And for this first one that I'm telling you is pretty easy, I need you to just notice that there is no I in the formula attached to the summation. It's not there. Okay, so this is going to be one of our easier ones. Okay, so with all of that said, how do we evaluate this? Well, to start with, we leave the limit alone. We're kind of working inside to out. Next, we leave the fraction alone. And finally, what we do is we replace the summation from I equals 1 to n of a constant with what it's equal to. Now, all of this, if I could circle it up in a different color like red or something. So all of this is one of the shortcuts that we just talked about on the previous video. It's a summation from I equals 1 to n of a constant 1. And what our shortcut rule said was that it's going to be equal to the constant times the top number, which is, again, n. All right? So there's using one of our shortcuts, formulas, to get, so essentially to replace the entire summation part of this with just something simple like 1 times n. Next, I need you to do the multiplication. So again, we're not messing with the limit right now. We're just going to multiply. And what's 1 over n times 1n? Well, the n's would cancel top and bottom. So what we're left with is 1. And finally, the limit as n approaches infinity of a constant. And in fact, it doesn't even matter that it's infinity in this case, because the limit as n approaches any number of a constant is just going to be that constant. So in your notes, here's what I need you to put together, that the limit as n approaches infinity for 1 over n times the summation from I equals 1 to n of 1, I need you to indicate somewhere for yourself that all of that's equal to 1. All of that is equal to 1. Okay? We've got 3 more of these to work ourselves through. This, again, is the easiest one, and we'll just keep plunking away. But we're trying to evaluate a combination of both a limit and summation. So feel free to pause the video at any point, but I'm just going to keep working myself through each of the 4. So here's the number 2. Here's the number 2. Once again, it's a combination of a limit. This, again, infinite limit. What we're taking the limit of is, once again, very strange. You'll understand it more over the next few days. But it's going to be this weird fraction, 1 over n squared, times the summation from I equals 1 to n. But this time, instead of a 1, Now we're going to be taking the summation of an I. Okay? And what we're going to do is evaluate this strange limit slash summation. Okay? And where do we get started? Like the previous one, we don't start with the limit. We don't start with the unusual fraction in front. Instead, what we start with is the summation. All right? We start with the summation. And the summation should look vaguely familiar because it's one of our shortcuts. All right, one of the 4 shortcuts we talked about for summations, the summation from I equals 1 to n of just a single plain old variable, in this case I. And what we do now is we replace that with what it's equal to. So you go back to your shortcut, and what is the summation from I equals 1 to n of I going to be? It's going to be the top number times the top number plus 1 divided by 2. So we replace everything in green with what the shortcut tells us it's equal to. Okay? Next, we do the multiplication. And when we multiply everything together, across the numerators, we have 1 times n plus 1, which causes us to use the distributive property, which is then going to be n squared plus n. Down in the basement, we just have n squared times 2, so that would be 2n squared. Okay? Now what we have in front of us is an infinite limit of a fraction. Infinite limit of a fraction. Let me choose a highlighter tool so I can really point it out. Infinite limit of a fraction. And we have to go way back to the fall to evaluate an infinite limit of a fraction. What we'll always do is multiply the top and bottom by 1 over the variable in the denominator that has the biggest power. The variable in the denominator that has the biggest power here is an n squared. So what we do is multiply top and bottom by 1 over n squared. All right, so we'll have the limit as n approaches infinity. The limit's still there. And then we distribute up top. 1 over n squared times n squared is 1. 1 over n squared times n is 1 over n. And 1 over n squared times 2n squared is 2. Pardon me. Everywhere you still see an n, replace it with infinity. Now we're evaluating the limit by everywhere we see an n, replacing it with infinity. But a fraction where the numerator is a constant and the denominator gets infinitely large has a value of 0. So what we end up with in the end is 1 plus 0 divided by 2, or 1/2. All right, so that's the process of getting there. But what I need you guys to then make sure is in your notebook is that the limit as n approaches infinity of 1 over n squared times the summation from I equals 1 to n of a plain old single variable is always going to be equal to 1/2. And this is the limit slash summation that I need to make sure everybody has down. Okay, so there's number 2. All right, and we're just going to keep plunking away. All right, we're going to do number 3. The third limit slash summation combination is going to be the following. The limit as n approaches infinity, once again an infinite limit, of 1 over n to the third times the summation from I equals 1 to n. This time we're going to have a variable squared. All right, so you can probably see kind of the steps that were taken. We started without any variable, then we had a variable raised to the first power, now we have a variable raised to the second power. Okay, so where do we get started? We do not begin with a limit. We do not begin with the fraction in front. Again, unusual, weird looking fraction, like where in the world is that coming from? Again, don't worry about it for right now. What we start with instead is the summation. All right, and this summation should look familiar from the first video because that summation is one of our shortcuts for a variable squared. And now just pick that shortcut off of your notebook, and the shortcut is the summation from I equals 1 to n of a variable squared is going to be the top number times the top number plus 1 times 2 times the top number plus 1 divided by 6. right? So we replace everything in purple with a shortcut, and now we need to multiply and divide. So what we'll have is the limit as n approaches infinity, 4. Multiplying the denominators is easy. N to the third times 6 is 6n to the third. The top, though, requires both a FOIL and a distributive property, so we'd have to FOIL the two binomials and then distribute the single n. So what we should get as a result is 2n to the third plus 3n squared plus 1n. And now I need you to do the limit part of this problem, so I'll switch colors on you. So now we need to do the limit part, which is the limit as n approaches infinity. And when we have an infinite limit of a fraction, to evaluate that, we multiply top and bottom by 1 over the variable that has the biggest power in the denominator. The biggest power of a variable in the denominator is n to the third, so we multiply top and bottom by 1 over n to the third. And what we'll get as a result, please notice the limit is still there. We distribute, boop, boop, boop. So 1 over n to the third times 2n to the third would be 2. 1 over n to the third times 3n squared would be 3 over n. And 1 over n to the third times n would be 1 over n squared. Down in the basement, 1 over n to the third times 6n to the third would be 6. Okay, so we simplify by distributing, and now we evaluate the limit by everywhere you still see an n, replacing it with infinity. So what we'll have is 2 plus 3 over infinity plus 1 over infinity squared divided by 6. And once again, whenever we have a fraction where the top stays the same, 3, and the bottom gets infinitely large, that fraction has a value of 0. So we end up with 2 plus 0 over 6. And when you add and reduce, you get a result of 1/3. And once again, what I need you guys to have down is that the limit as n approaches infinity for 1 over n to the third times the summation from I equals 1 to n of a variable squared is going to be 1/3. Right? That's the limit summation that we're going to be using multiple times. Okay? Whew. And finally, we have one more of these limit summation problems. Okay, so here's the last one. So here's number 4. And you probably, well, I don't know, maybe you've seen the pattern, but we'll have the limit as n approaches infinity, weird fraction again. This time it's 1 over n to the fourth, for the summation from I equals 1 to n of a variable cubed, raised to the third power. Once again, we will not start with the limit. We will not start with the unusual fraction. What we'll do instead is we'll start with the summation. Okay, and again, the summation should look really familiar. It's one of our shortcuts. So the summation from I equals 1 to n of a variable cubed is going to be the top number on the summation, n, times n plus 1 divided by 2 squared. All right, so again, what we've done is replaced everything in purple with the shortcut. And what we need to do before we can evaluate the limit is we need to do the multiplying and dividing. Okay, so first, of course, you always have to square first and then multiply by the 1 over n to the fourth. And what we should get is 4n to the fourth down in the bottom. That one's a little easier for me. And then up top, when I distribute and square, what I would then have is n to the fourth plus 2n to the third plus n to the second. Right? And to evaluate an infinite limit, we multiply top and bottom by 1 over n raised to the largest power you have in the denominator. In this case, that's n to the fourth. And when you distribute, please notice the limit is still here. Okay, so when we distribute 1 over n to the fourth times n to the fourth, we get 1. 1 over n to the fourth times 2n to the third would be 2 over n. And 1 over n to the fourth times n squared would be 1 over n squared. Down in the bottom, 1 over n to the fourth times 4n to the fourth would be 4. right? And now that we've simplified, now we can do the limit by replacing n with infinity. So we'll have 1 plus 2 over infinity plus 1 over infinity squared divided by 4. And once again, fractions where the top stays the same and the bottom gets infinitely large become 0. So 1 plus 0 over 4, which obviously is 1/4. Okay? And again, what I need you to have down is the following. The limit as n approaches infinity of 1 over n of the 4th times, oh, lovely summation, we'll try that again. The summation from I equals 1 to n of a variable cubed is going to be equal to 1/4. Okay, so those are the four special limit/summations that we are going to be using, Okay? Alrighty, so those are kind of tough to get through. A lot of work, a lot of kind of combination of new stuff and old stuff. But what this then leads us to is the beginning of a more economical way to find the area under a curve. We're going to be combining these summations, these limits, into being able to calculate the area, exact area, under a curve. Right? So that idea that we've been talking about now for a little while, we're going to be trying to find all of this area underneath a curve on an interval without approximation. So we're going to be figuring out a way to do this exactly. Right? So we're going to be finding this area. Okay, so that's what we're heading toward. So I'm going to stop this video now. I don't know if it's worth, you can definitely try some of the easier initial problems in the assignment, but when I get back tomorrow then, we're going to move on to how to calculate this area. Okay? So, we'll talk to everyone tomorrow. Hope you're having a good day.